Hello, welcome back. The title of this lesson is called Atomic Theory of Matter, and this is part 1. So in this lesson, the purpose of it is to kind of take a historical glance back at what we know about the structure of matter. And the good news is you already know a lot of what is already in this lesson because you already were taught when you were young that everything around you is made up of atoms, and everybody knows this in the modern age. But the purpose of this lesson is to travel back in time to the beginning of the 1800s when people didn't know that the structure of matter was composed of these tiny little things that we now call atoms. And we're going to talk about what was put forth as the atomic theory of matter back then, which by and large, with a couple of exceptions, really carries over into the modern day. So everything we're talking about, even though it was discovered a long time ago, is applicable today. And then as we go on further in the lessons, we're going to zoom into the atom itself and talk more about the structure of the actual atom. Because I know that you also know that atoms are made up of smaller things, protons, neutrons, and electrons. And now in the modern age, we know that the protons and the neutrons are actually composed of even smaller things called quarks. So it's like going down the rabbit hole, right? Deeper and deeper down the rabbit hole. But for the purpose of chemistry, we don't really care about what the proton is made of, right? What we really care about are the elements and the atoms, because those are the things that combine together to give us all of the variety of the substances that we know and we see around us, okay? So again, put yourself back in the frame of mind from someone a couple of hundred years ago, 250 years ago. You know that there's something called water. It's all over the planet, and it's refreshing, and it's cool, and you can pour it, and it's a liquid, okay? And you know that if this water, if you leave it out in the sun, it will start to disappear. It'll evaporate. And you think it's in the air, but I mean, you really don't know, but you suspect it's floating in the air somewhere. But it's certainly not something you can pour anymore, okay? And you also know that you build fires. And if you take, for instance, charcoal, which they didn't use charcoal too much back then, but if we can use the concept of charcoal, which is mostly carbon, just carbon, and if you burn it, then what ends up happening after the burning process is over is you have ash left behind, and then of course the smoke has gone up into the atmosphere, right? Now, all of these different processes people were observing all the time, right? You can see things changing around you. If you put iron outside, it's going to rust. It's going to change in its luster and its appearance and things like this. If you burn something, it's obviously going to change its appearance into something totally different looking. If you burn wood, then the ash that's left behind is completely different looking. If you were a scientist and doing experiments, you might take something that you think is hydrogen, and which is a colorless gas, and you would react it with something called oxygen, which is another colorless gas. And even though you start with two colorless gases, when you react those together, what do you get? You get water, which is not a colorless gas. And it pours and it flows, and we drink it all the time. So even though hydrogen is not something you drink and oxygen is not something you drink, once they are into this new thing called water, then it's something that we drink and we need. So for the longest time, millennia, people just thought that the universe was a bunch of different, essentially materials, right? That water was different than, we didn't really know what water was made of, is what I'm trying to say. It was just a new substance. Of course, there were the theories of earth, fire, wind, and water, and those are the fundamental elements, and everybody had their own pet theories. But by and large, until we came up with an atomic theory of matter, all the different substances that you see around you, they just look totally different from one another, okay? So as experiments were performed, and scientists really started combining things and seeing what was created and produced as a result of that. We now call that chemical reactions. Then they started to deduce how this kind of situation would come about. And so now what was put forth by a scientist named John Dalton in the early 1800s is what we call the atomic theory of matter, and it explains the great variety of things we see around us in terms of building blocks that we now call elements or atoms. Same word, or same meaning, different word, okay? So what I'm going to do is I'm going to read to you, I'm not going to write it all down, Dalton's atomic theory of matter, and with the exception of one thing at the end I'll talk to you about, basically everything on this list is applicable to what we already now know to be factual, okay? And then after that, we're going to talk about a couple of important observations that were studied back in the day in early scientific discoveries. And we're going to learn about those. Those are called the law of conservation of mass and a few other things that are all directly still true and applicable to chemistry today. So Dalton's atomic theory, you can call this a classical atomic theory. Again, these scientists didn't know anything about the structure of an atom. But what was put forth as an explanation for all the things that are around us, the different variety of things, is instead of there being an infinite variety of things, leaves and trees and gases and liquids and solids and water and water vapor and everything being separate, we instead it was instead proposed by Dalton that everything, every piece of matter that you can touch is actually made up of a relatively small number of what they called indivisible elements called atoms. Now we know that atoms are divisible. We can split an atom. But for now, just put that aside. Of course we can split the atom, but you can't do that with chemistry. You have to use nuclear physics, and that's another topic for another day. The word atom is meant to signify that it's an indivisible thing. In other words, if you get down to a single oxygen atom, if you start cutting your sample of oxygen, or carbon, let's call it carbon, you cut your sample in half and half and half and half, eventually you get to one carbon atom. You can't split a carbon atom anymore, because if you do that, it won't be carbon anymore. It'll be something else. It'll be some other nuclear decay or something we'll talk about in the future. But these things are called indivisible because they retain the character of the elements. Okay? And we now know the periodic table is about 100 elements. Of course, there's some heavier ones. It really goes up to about 118 elements. But those are, the last ones are radioactive. We don't talk about them too much because they're not naturally occurring in nature. By and large, we say the periodic table is on the order of about 100 elements, and everything you see around you is just different combinations of those elements. That is the fundamental nugget of atomic theory, or the atomic theory of matter as put forth by Dalton, is that instead of there being a million different varieties of substances just happen to be on Earth, everything is made of a finite number of ways in which you can combine these really and truly indivisible things, which we call atoms. So number one, matter in the universe is made up of elements, which are essentially atoms, and these atoms are indivisible. That's number one. Number two, all atoms of a given element are identical in their properties. So if you have a bucket full of carbon atoms, every carbon atom is identical to another carbon atom. Every oxygen atom is identical to another oxygen atom. There is no difference. They're completely and totally interchangeable with one another once you have down to that level of knowing what kind of atom you have. But different atoms of different elements have different properties. For instance, we know that carbon has a certain mass for each of those atoms, and it has a certain boiling point and a melting point, all its physical properties, what it looks like, things like that. But nitrogen is a totally distinct atom, which is different, and it has its own properties, which are, its own boiling point and melting point and its mass and its electrical conductivity and all these other things. So all of the carbon atoms are essentially identical. All the nitrogen atoms are essentially identical, but they are different and distinct from one another. Now, as we go further in the class, we're going to talk about what makes them distinct from one another, but I'll give you the punchline right now, and that is that these two different atoms have different numbers of protons and neutrons and electrons that they are comprised of. That is what makes them different. Right? We'll talk about that later, but for now, just know that you have different atoms and they have different characters, and that makes them distinct from one another. So if you want to use the cartoon, the little ball analogy here, so we have a red atom here, right? It's not really red, but we say that this is an oxygen atom. It has a certain mass. If you have a bunch of these things together, you can measure its boiling point, its melting point, its conductivity, its flammability, its density, all the things that we can measure, we can ascribe to this thing, which is an oxygen atom. Then we have a white one, which we call a hydrogen atom. And of course, it's not really white. We just paint it white so we can tell the difference here. And all of the hydrogen atoms, again, have all the same properties, the density and all the other characteristics, and they're all essentially identical to the other hydrogen atoms. And everything in nature is just different combinations of how we can combine all of these different elements on the periodic table. The most famous of which, of course, is water. And we're going to talk about this a lot later. Of course, we're not done with water, but we have oxygen, and we have connected to it with these little sticks here, we have the two hydrogen atoms, so H2O, right? But hydrogen and oxygen do not have to combine with each other in these ratios. In other words, 2 hydrogens for every 1 oxygen. In fact, if you stick another oxygen on the end of this thing, you'll have H2O2, which is not water, that's hydrogen peroxide. And of course, you can combine these things in other ways and come up with other, what we now call molecules. So the fundamental atomic theory of matter is saying that everything around you, the difference between H2O, hydrogen peroxide, and water is basically the amount, the number, and the type of the elements that are all connected together, if you could get in there and zoom in on it and look at it. So number one, elements are made up of extremely small atoms. Number two, all atoms of a given element are the same. Number three, different elements have different properties. Of course, we know this. And here we are at number four. We cannot change atoms into different atoms by chemical reactions. People tried to turn lead into gold for many, many, many years because they wanted to get rich, because gold was valuable. And they want, we see things changing all around us. So it was perfectly logical. We see iron rusting, for instance, right? We now know that's combining the iron with the oxygen in the air. But people didn't know about the atomic theory back when they were doing alchemy. So they were taking a heavy metal called lead and trying to change it into another element called gold. And that's just not going to work. Not by chemical reactions, okay? We now actually can do weird things like this, but we have to use nuclear reactions where we rip apart the atom and we change the actual atom's structure by either adding protons or taking them away or whatever. So we can do lots of things now, but chemical reactions do not change the types of atoms in the chemical reactions. Chemical reactions, we're going to learn later, is basically all about the transfer of the electrons, which are on the outside of the atom, and rearranging the atoms into different combinations, and transferring those electrons and rearranging the atoms. That's what we do here. We cannot change one element into another. That is an element or one of the propositions of the early atomic theory. Number five, atoms can neither be created nor destroyed in chemical reactions. This is one that took a long time for people to really understand and start to believe. So if you believe that everything is made of these fundamental atoms, can you destroy one? How would you? Well, it turns out that you can't. And we call that the law of conservation of mass. We're going to talk about it more in a second. But in a chemical reaction, whatever you start with, if you know all of its mass, and then you do the reaction and you collect everything on the other end. And if you measure the mass of everything after the reaction is over, then the beginning mass should be exactly equal to the ending mass. Because if a chemical reaction is just rearranging the atoms, it's like different Legos. If you rearrange the Legos, then you should still have the same number of Legos before and after. And it turns out that that is true. If you're very careful in measuring the mass before and after reaction, you'll find that the mass is always the same before and after. Now things get tricky when you, for instance, burn wood in a campfire. But if you're careful, you see, what's going on when you burn the wood is you have the ash left behind, but some of that carbon is combining with oxygen and it makes CO2, carbon dioxide, and also carbon monoxide, CO, and also water, H2O. And those things float up into the air and they disappear. You can see it coming up, well, you can't see the CO2, you see the soot coming up, you see that. But the CO2 and the CO and even the water vapor are basically invisible. But if you could collect everything floating up from the campfire and also collect the ash, and we're very, very careful about it, then you would find that the mass before and the mass after the reaction is over is the same. That is another proposition set forth in the atomic theory of matter, as put forth by Dalton. All right. Number six, reactions only rearrange the atoms. We talked about that. And number seven, compounds form when atoms unite, which we call bonding in a modern language, in fixed whole number ratios. So this is a biggie. This is a real biggie. So at first you have to hypothesize that everything is really not different. Everything is really made up of a small number of little things called atoms. But that these atoms can bond together and connect together in only whole ratios. What that means is, if I want to bond, an oxygen to a hydrogen together like this, it has to be 1:1 or 1:2 or 1:3 or 1:4 or 2:4 or 2:6 or 1:8. It has to be a whole number ratios because you have to have an entire oxygen atom or an entire hydrogen atom in order to bond. In other words, you cannot cut an atom in half and have the chemical reaction. Everything is bonding in whole number ratios because the atoms are whole things that cannot be basically split in half. Now, of course, we know now that we can split atoms in half, but that's not chemistry. That's nuclear physics. That's not a chemical reaction. So we're ignoring that for right now. So real quick from the top, these are all things that you should kind of know from earlier things, but we're codifying it into what we now call the atomic theory of matter. Number one, elements are made of extremely small atoms. Number two, all atoms of a given element are identical. Number three, different atoms of different elements are different. Of course, their properties are all different and distinct from one another. Number four, you cannot change from one atom into another atom by chemical reaction. That doesn't happen. Number five, atoms are neither created nor destroyed in chemical reactions. Number six, reactions only rearrange the numbers of the atoms you have that are reacting together, like Legos. And the last number here, seven, compounds form when atoms unite in whole number ratios. You can't split an oxygen in half. It has to be one and then a fixed whole number of something else bonding with it. That's the atomic theory of matter. All right. Now, right on the heels of that, as I said, lots of experiments were done where they would take certain chemicals, and we could see, or they could see back then, that they reacted together and they could collect the products. So they didn't really know in the beginning that it was small little indivisible atoms. That came later, but they did a lot of experiments with how much mass reacted with how much of something else and how much was produced for the products. They did a lot of calculations and collecting of data. And so I'm not going to write this one down either because this is so, I think, something that everybody mostly knows, but if not, it's not that hard to understand. We already mentioned it. It's called the law of conservation of mass. And that says that the total mass before the reaction is equal to the total mass after the reaction. So if I wanted to say conservation, I just said I wouldn't write it down, but here I go. The conservation of mass. We now you can write this as a big sentence if you want to. I could just say the mass before reaction, Rxn is reaction, is equal to the mass after reaction. But you have to be careful because if you're burning something, you have to collect all the gases. If you just have to be very careful and meticulous. But the mass before is always equal to the mass after in a chemical reaction. All right, so that's Dalton's atomic theory of matter. It's all true with the exception of when it talks about that you can't turn one atom into another. That's true. You can't do that with chemical means. But now that we know that atoms are made up of smaller things, of course we can break atoms up. We can add protons. We can create some of these elements in the laboratory by shooting protons in an accelerator. So we actually can fiddle around with, I don't want to say changing one element into another, but certainly altering what an atom is by either injecting protons and electrons and doing other things in high energy accelerators. But that is not chemistry. Chemistry is all about electron transfers and rearranging what the atoms are. So now what we have to do is go and talk about two more laws. I'm going to show you what they are. We're going to read them, and then I'm going to explain. They're much easier to understand with an example. The first one is the following. And again, you might think this is obvious, and that's just because you were born understanding this from second grade. You were learning what atoms were. There is something called the law of constant composition. All right. You might also see this written as the law of definite proportions because it has kind of two different names. But it's the law of constant composition. It says that all samples of a compound have the same composition, which are the ratios of the elements that are present there. So what I mean by that is if I take H2O by mass, if I meticulously measure how much hydrogen is in this water molecule and how much oxygen is in this water molecule by mass, by the way, how would I do that? I would take a bucket of water and I would have to break up the water molecule. Right? And we know we can actually do that by passing an electric current through the water molecule. And you'll see bubbles forming on one wire and other bubbles forming on the other wire, and those bubbles are the hydrogen and the oxygen gas. So if you're really careful and you do this experiment without blowing yourself up, so don't do it, all right? Don't do it because it's flammable. Hydrogen is very flammable. But if you're careful and you collect the oxygen and the hydrogen, what you're going to, and if you suppose that that's coming from the water, which is in the liquid form there, then what we find when we do that experiment and collect everything and measure its mass is the mass percent of hydrogen in water is approximately 11.11%, and the mass percent of oxygen in water is approximately equal to 89.99%. Right, so what this means, the law of constant composition means that no matter if I take a bucket full of water from this part of the bucket, or from this part of the bucket, or from this part of the bucket, all water molecules are the same. And if I can peer inside and see what they're made of, and now we know they're made of hydrogen and oxygen in these ratios, then what we find out is that if we break it apart and do the experiment, we might find that the mass of the water turns out to be only 11% hydrogen in terms of its mass, and almost 90% oxygen in terms of its mass. And no matter how many different samples we take of different buckets of water, we're always going to get the same exact ratio of hydrogen and oxygen by mass. That's the law of constant composition. It basically just says all samples of the compound have the same composition, which is the ratio of the atoms. And that is because they're all made of the same atoms, and the atoms are all identical. And so if we all know they're all made of H2O, and all the hydrogens are identical in the universe, and all of the oxygens are identical in the universe, then we know when we measure the percent mass of any compound, no matter where the sample comes from, we're going to get the same answer all the time. Constant composition. All right? Now notice that we now know that water is H2O. So there's actually 2 atoms of hydrogen and 1 atom for oxygen. So there's actually more hydrogen in the atom in terms of the actual atoms. There's 2 atoms of the H's, the hydrogen, and 1 of the oxygen. So the 2-to-1 ratio of hydrogen to oxygen. But the mass percentage of hydrogen is really small, and the oxygen mass percentage is really, really high. How can that be? How can we have way more hydrogen, double the amount of hydrogen atoms, but yet have much less percent of the hydrogen by mass? Well, you probably realized it, that if you were to go to the periodic table and look for the mass of the hydrogen, it's a much less massive atom than oxygen. In other words, oxygen has more protons and neutrons in there that make it more massive. So even though the molecule itself only has 1 oxygen atom and 2 of these hydrogens don't have much mass at all. So when you add it all up, it works out that the hydrogen actually only accounts for about 11%, whereas the oxygen counts for much more. So these atoms are combining in whole number ratios, which we now call molecules, but all of these atoms have different masses. And so constant composition, no matter how many samples you take, you're going to get the same ratios by mass or by the number of atoms, no matter where you look. Remember, back in 200 years ago, they couldn't zoom in and look at the atoms. I mean, we can't even really do that now, right? We have some images of atoms, but I wouldn't say they're really images. They're more of graphs of showing the results of a experiment more than anything. It's not like a visible light picture. You can't really see atoms so easily. I mean, like I said, there's some experiments, but they're not like color photographs of atoms. What we really can do is measure the mass when we break apart water. So the constant composition is more related to the mass. Is going to always give you the same ratios. Now that's pretty easy to remember. The law of conservation of mass says the mass before a reaction is equal to the mass after. The law of constant composition just says you're going to get the same percent masses by element, no matter how many different times you do the sample or where you get the sample from, as long as the material is the same. These are fairly easy to understand. This one right here is the one that is much, much more difficult for most students to understand. So we're going to read it several times, and then we're going to talk about it with a real example. So here it is, the law of multiple proportions. We're going to read it a few times. When 2 different compounds of the same 2 different elements are compared, the mass of one element that combines with a fixed, underline fixed, mass of the other element, the second element, are in the ratio of small whole numbers. Now, I know what this means, but every time I read it, it noodles my brain. The words just jumble and it doesn't make a lot of sense. So let's read it one more time, and then I'm going to show you with an example, and you're going to be like, oh, I got that. That makes sense, after he writes down an actual example. So, when 2 compounds of the same 2 different elements are compared, the mass of one element that combines with a fixed mass of the second element are in the ratio of small whole numbers. Basically, what this boils down to is it's essentially telling you that these compounds are always going to combine in ratios. Like we know that we can get H2O, right? And we know that we can get H2O2. That's hydrogen peroxide, right? We know that we can get We know that we can get CO, carbon monoxide. We know that we can get CO2, carbon dioxide. There's many examples I can list here. You can change the subscripts. You can increase the number of atoms, but you can never have CO 1.5. You can never have C 3.72. You can, and you know that intuitively because you know that there are these things called atoms and they're like Legos and they have to combine. But back in the day, they didn't really know that. So this is basically a law that essentially predicts that these elements are combining in whole fixed ratios. That's why it's called the law of multiple proportions. Proportion is related to the word ratio. And it basically, when you boil it down, it basically says that when you combine different elements together, they're going to combine in whole number ratios. And when we do experiments to measure the amount of mass in each of the different molecules that we create, we see that they're related to one another. So let's give a good example, I think. Let's give a couple of examples of this, okay? Let's take the compound carbon monoxide. Right? Carbon monoxide is going to be right here. And then we're going to say CO2. That's carbon dioxide right here. And I'm going to put a little squiggy right in the middle so I hopefully don't bleed over into one column from another. So let's say we do some experiments and we figure out that this is 3 grams of carbon and we add it to 4 grams of oxygen. That's what we start out with 3 grams of carbon and we figure out by reacting it that it only soaks up 4 grams of oxygen, not 5, not 6, not 7. It only reacts with 4 grams. And of course now we know it's because the masses of these things are fixed and the way in which they can react, or they have to be whole numbers, so it can't just react with 4.5 grams or 6.72 grams. It's only going to join together in certain ratios because the atoms have fixed masses and we can only combine these atoms in whole number ratios. But they didn't know that at the time, so they wrote this law down back when all this was being discovered. All right. Now, for the carbon dioxide, let's say that we start out with the same 3 grams of carbon, right? And because the molecule has an extra oxygen, actually what happens is 8 grams of oxygen is what reacts to it. Now, reacts with it. Now, I think this should make sense to you, right? Because we see the only difference between these molecules is there's an extra oxygen atom. And since you know that each oxygen atom is the same, if you double the number of oxygen atoms, you should double the amount of mass that reacts with the fixed amount of carbon. Notice that I started with 3 grams of carbon in each case to make it easy to compare. Because these are the same, then if you have 4 grams reacting of oxygen here, you should have double the amount, 8 grams reacting here. So here it says when 2 compounds of the same 2 elements, carbon and oxygen, are compared, the mass of one element that combines with a fixed mass of the second element. Notice it's a fixed mass here, are in a ratio of small whole numbers. All right. So what we figure out after we allow this reaction to occur is that what you get, I'll put a little arrow for like an equal sign, you get 7 grams of CO, right? Because you start with law of conservation of mass. 3 plus 4 is 7. You have to have 7 grams of the product. And when you let this thing react, what do you think is going to happen here? You should get 11 grams of something called CO2 because you add these together and you get 11. So far everything makes sense. This is kind of what you would expect. What we want to do is I want to rename this law in your head. Instead of calling it the law of multiple proportions, I want you to call it in your head ratio of ratios, because that's really what you're doing. If I had to name it, I know it's kind of a silly name also. It's not a great name. But if it were me and I were trying to be descriptive, I would actually call it the ratio of ratios law, because this is what we're going to do. What we're going to do is we know how these things, what ratio these react in, and we know what ratio this other compound reacts in. I want to figure out, I want to write down the ratio here and the ratio here of how they react, and I want to compare these ratios together, and we're going to find out something interesting. So what you want to do is write down this ratio, but you always want to do the top number and divide it by the bottom number, because remember, when you write down ratios, you need to write them down as a fraction. That's a ratio. So since 4 is bigger, I'm going to put 4 grams of oxygen on the top in a ratio with 3 grams of carbon right here. And when I take 4 and divide by 3, notice I put the units. 4 grams of oxygen is locked in a ratio with 3 grams of carbon. Okay, so 4 divided by 3 comes out to 1.333. Now, the 3's go on forever. I'm truncating it at the 3rd position here. then what are the units I have here? I have grams of oxygen per grams of carbon. So what this means is that 1.333 grams of oxygen react for every 1 gram of carbon, because that's what the units tell me. Yes, it really was 4 grams reacting with 3 grams. But when you do the division, it's like going 100 miles or 100 kilometers in 50 seconds. Yes, you actually went 100 kilometers in 50 seconds. But your speed is better when you, to really compare everything the same, you actually do the division. 100 divided by 50 is really 2 kilometers per second there. So 100 kilometers is the same thing as 100 kilometers. So if you do 100 kilometers in 50 seconds, then when you divide this, this comes out to 2, and the unit is kilometers per every 1 second. 2 kilometers per every 1 second. So we really reacted 4 grams of oxygen with 3 grams of carbon. That's the ratio, but that's the same thing as 1.333 grams of oxygen for every 1 gram of carbon. That's the ratio of the reaction that's going on here, okay? Now let's do the same thing. Big number divided by small number. 8 grams of oxygen in ratio with 3 grams of carbon. What is 8 divided by 3? You get 2.667, and the units are still here. Grams of oxygen per grams of carbon. So this one reacts in the ratio of 2.667 grams of oxygen per every 1 gram of carbon. So what the law of multiple proportions says is that if we find the ratio that's happening in this reaction and the ratio that's happening in this reaction, which we just figured out, and we compare these ratios, 2.667 compared to 1.333, you're going to find something interesting. Again, we take big number divided by small number. So 2.667, and what was the units here? It was grams of oxygen per grams of carbon. And we're going to put that in ratio or divide with the other one. We're comparing 2 different molecules. 1.333 grams of oxygen per grams of carbon. Now we have the exact same units on the top and the bottom, so just like any unit conversion, they're going to cancel. And what do you get when you take 2.667 divided by 1.333? You get exactly 2, the number 2. And the number 2 can be written as a fraction 2 over 1, which can be written as a ratio of 2 in ratio with 1. What it's saying, that's why I said I want to rename this thing to the following. We call it a ratio of ratios. We take the ratio of how this molecule reacts, the ratio of how this reacts, and then we get those answers and we take a ratio of those, and the answer always comes out to a ratio of whole numbers, right? Of small whole numbers. So now that we've done this, let's read the thing again and see if it makes any sense. When 2 compounds of the same 2 elements are compared, 2 compounds, same 2 elements, carbon and oxygen, are compared. Of course, the subscripts are different, but it's the same 2 elements, and we are comparing, so we're good up to here. The mass of one element that combines with a fixed mass of the second element, that is a wordy way of saying take the ratio of the things that are reacting together, of the second element, are in the ratio of small whole numbers. So we take these ratios and then we take these 2 numbers and put them in ratio, and we always get a whole number there. Now, that's great, but why do we care? You got to put yourself in the position of someone who doesn't really know about atoms. You take some carbon and you let it react with oxygen. You might think that it's always going to react the same way, but it doesn't, because some of the times it reacts to make this, and some of the time it reacts to make this, but you don't know that. All you know is that you get some mixture of results, one of which looks different than the other. And when you actually measure the masses and the composition of what you get as the products, you figure out that sometimes it reacts in a ratio of 3 grams of carbon to 4 grams of oxygen to make some product. And then sometimes it reacts with 3 grams of carbon with 8 grams of oxygen to make some kind of product. And you know that these must be different substances somehow, but you're not totally sure about the atomic nature of what's going on. So what you find out is, if you were really going to study this for the first time and try to figure out the atomic theory, what you would do is you would look and see how they compared, how do they react together? How much of carbon reacts with how much of the oxygen in terms of mass and grams of what you mix together to react. That's what you would do. You would try to see how they react. And you would say that the ratio of this reaction is 1.33 grams of oxygen to 1 gram of carbon. But sometimes you mix it together and it mixes and it reacts in a ratio of 2.66 grams of oxygen to carbon. And you scratch your head and you say, why is it different? Why is it different? What could possibly, because you're assuming that it's always making the same product the whole time. But then you realize every time you do this reaction, an experiment, the ratio you get here is exactly double the ratio here. And you see that because when you divide them, you always get a number of 2. And then you do the same exact reaction or the same exact procedure with something else, maybe nitrogen combining with oxygen. So after you get this interesting result, you try to do the same thing with maybe 2 other different elements that make multiple different compounds. And you find out that this result occurs and happens repeatably and reliably all the time. That whenever you figure out how 2 things combine in terms of their mass, and then find out how they combine in a different way to make a different substance, and you take these ratios, you always find that this ratio is related to this one by a ratio of whole numbers. In other words, it's not random ratios you get, they're related to each other. If you were going to use that to formulate an atomic theory, which they did, what would it cause you to think? It would probably cause you to think that the reason that the different substances that are created are basically made of building blocks that can only combine in certain ways. Because what this thing is really telling you, when you get a ratio of 2 here, 2 to 1, where this is the number over here and this is the number here, the units are grams of oxygen compared to grams of carbon. Grams of oxygen compared to grams of carbon. What it's telling you is that there's twice as much oxygen per gram of carbon in this molecule. I'm going to say that again. Because the ratio is 2 to 1, it means there is exactly twice as much oxygen as compared to carbon in this molecule compared to this one. And the way that that happens is if the oxygen can only come in discrete chunks, which we now call atoms. Oxygen cannot be added to the molecule just any which way you want. You can't just add a fraction of an oxygen substance to it. It only comes in chunks, which we now call atoms. And that leads to atomic theory. That's why this, even though it's a little wordy, and even though it's a little weird, it's always taught in chemistry classes because it basically leads you to conclude that atoms are combining and making these different compounds. Even though maybe the compounds behave differently and have different masses, they're made of the same underlying things in fixed ratios. So let's take that before we close out this lesson and do the exact same thing that we just did over here with, instead of CO2 and CO, let's take a look at nitrogen combining with oxygen, NO2, and nitrogen combining with oxygen, N2O. So these are 2 completely different compounds, but they both contain nitrogen and they both contain oxygen, and they're going to have obviously different masses. So we can use the law of multiple proportions. Let's say that for the NO2, what you end up seeing when you do the experiment is that 2.28 grams of oxygen combines with 1 gram of the nitrogen. Okay, this is the ratio, this is the amounts that are reacted together, right? When you supply 1 gram of nitrogen, this is the only amount of oxygen that reacts with it, not 2.5, not 2.7. This is the amount that reacts with 1 gram of nitrogen. And you do the same thing over here. You find out that 0.570 grams of oxygen combines with 1 gram of nitrogen. So when you make this substance over here and you again supply 1 gram of nitrogen, it only takes up and reacts with this much oxygen, not 0.6, not 0.8, not 0.9, only this amount, okay? So if you were going to study how these were related to each other, what would you do? You'd probably want to figure out the ratio of these 2 things that are reacting together. Bigger number divided by smaller number. So you would say 2.28 grams of oxygen in a ratio with 1 gram of nitrogen, right? And then over here, you do the same thing. And even though I usually say bigger number divided by smaller number, we have to write the ratio in the same top and bottom numerator. So over here, we're going to write 0.570 grams of oxygen in a ratio with 1 gram of nitrogen. Now, this one's easy because there's only a 1 on the bottom. So when you divide it, you get 2.28, and the units are here as grams of oxygen compared with grams of nitrogen. And then over here, you're dividing by 1, so you get 0.570 grams of oxygen per gram of nitrogen. So what this is saying is when you react and make this compound, it's 2.28 grams of oxygen for every 1 gram of nitrogen. That's the ratio. And this is 0.570 grams of oxygen for every 1 gram of nitrogen. So these are the ratios that we have here. What the law of multiple proportion says is that once we have these ratios themselves, when you divide one by the other, should be a whole number, a fixed ratio of whole numbers. All right? So what we do then is we come down here and we say, all right, what is 2.28? And let's go ahead and put the units. Grams of oxygen per grams of nitrogen in ratio with what we have over here, 0.570 grams of oxygen per grams of nitrogen. So we have this unit canceling completely with this unit, so you have a dimensionless result. If you take 2.28 and divide by 0.570, you get exactly 4. And you know that the number 4 is the same as 4 over 1, which is the same as 4 in ratio with 1. So what did the law of multiple proportion say? It says when two compounds of the same two elements are compared, the mass of one element that combines with a fixed mass of the second element are in ratio of small whole numbers. What it is saying is take the ratios that combined, the ratio of each of the different molecules that form, and then put those two numbers in ratio. It's a ratio of ratios. Here, we found the ratio was 1.33. Here, we found the ratio was 2.667. Put those in ratio, we get 2 to 1. And that meant that there was twice as much oxygen as compared to carbon in the second molecule. When we do the same exact thing here, we take the ratio of these, we take the ratio of these, and we take these numbers and put them in ratio, and we get exactly 4 to 1, which means this one has 4 times the amount of whatever's on top, oxygen, as compared to nitrogen. This means this molecule has 4 times the amount of oxygen by mass as it does nitrogen when you compare it to the other molecule. Now, does that make sense? I mean, it made sense here because what we basically said is CO2 has double the amount of oxygen as CO. That makes sense. But this one's a little harder to look at. What we're claiming is that this molecule has 4 times the amount of oxygen because oxygen's on the top as compared to this one. Well, it's tricky because you see this one is in with only 1 nitrogen and this one has 2 of them, so that makes it a little tricky to compare them. What you really need to do is divide this, even though we can't break an atom up, we can mathematically divide this by 2, so we can have nitrogen each having a number 1 here. So if you divide this by 2, what you'll get is N1 and then oxygen 1/2. If you divide each number by 2, oxygen will be 1/2. Now I know that you can't cut an oxygen atom in half. I know that, but mathematically you can still divide them and say, okay, if this can become a 1, then this can become a 1/2. And since the nitrogens in both cases then would have a 1, you would have a 2 here compared to a 1/2 here, and then this would be 4 times bigger than a 1/2. 1/2 times 4 is 2. So when you put them on equal footing and make this, when you divide by 2, if you make it N1 oxygen to the 1/2, then this molecule is indeed 4 times more oxygen by mass when it's compared to nitrogen as compared across the different molecules. So we covered a lot in this lesson. We covered the historical evolution of atomic theory. We first just kind of outlined what the atomic theory is, and it should seem fairly familiar to you because we're all grow up now knowing that everything's made of atoms, but once upon a time, not too long ago, nobody knew atoms existed. They just thought there was an infinite variety of amazing different things out there, and we didn't really know why they existed. And even things that look different from each other, we now know it just depends on how the atoms combine to make their properties different. For instance, sodium. Sodium is an element on the periodic table that's a metal and it reacts violently in water. Okay, it actually it generates a lot of heat and it reacts violently with water. Chlorine is, at room temperature, a gas that will kill you. But if you put them together, you make something called sodium chloride, which it's not a metal at all, and it's not anything that's going to kill you, like chlorine will kill you. It's something we eat every day. So the properties of the substance change dramatically after we combine them together. And that idea that everything is made of a small amount of building blocks really set off the modern age of chemistry. The rest of the lessons here, we're all just trying to kind of like give you a little practice with how we applied this thing. And the 3 most important are the conservation of mass. The mass before the reaction will always be equal to the mass of everything that you collect after the reaction. Constant composition means if you measure the ratios by mass of any sample of a compound, you're always going to get the same ratios because all of the molecules in the compound are all basically identical little molecules or compounds that are joined together. We know this because they're joined based on individual atoms together. And then the constant, or the law of multiple proportions, is basically another way of saying that all of these molecules that we find in nature are just various combinations of these things called atoms. or elements, same thing, right? And so that was a great deal of proof for the theory of atomic theory of matter. So I'd like you to watch this probably 2 times, maybe even 3 times, to make sure you understand what is being said here. Then follow me on to the next lesson. We're going to solve a few mathematical problems to get practice with these ideas.